Good afternoon, everyone, and thanks for coming to ESO and for joining us online. We have some remarkable observations to report today. I'm Richard Hook, Public Information Officer here at ESO in ESO headquarters in Germany. The format of today's press conference will be as follows. First, we'll connect to ESO's Paranal Observatory in Chile, and ESO's Director General, Xavier Barcons, will make some welcoming remarks. We will then hear from several of the lead scientists involved in these discoveries. They are Stephen Smart from Queen's University, Belfast, in the United Kingdom, Samaya Nisanka from Radboud University in the Netherlands, Elena Pian from ENAF Bologna in Italy, Marina Rekuba from ESO here in Germany, and Andrew Levin from Warwick University in the UK. We're also pleased to have some other experts in the room who will be available for questions and potentially interviews. This is Stefano Covino from ENAF Brera in Italy, and Maddalena Mantovani from the Virgo project, also in Italy. After all the presentations, journalists will have an opportunity to ask questions, first here at ESO, and then we'll have some submitted by email. So, to start with, let's go over to Chile and hear from ESO's Director General, Xavier Barcons.
Hello, good afternoon, everyone. Can you hear me?
Or maybe...
Hello, can you hear me? Can you hear us, Richard?
Yes.
Okay,
yes,
good.
We can hear you. Go ahead.
Thank you very much. Good afternoon. It's a great pleasure for Andreas Kaufer, who is the director of the Observatory, sitting next to me, and myself to welcome you to this ESO press conference from the VLT control building, actually, where many of the very relevant observations to the discovery being reported today were taken a few weeks ago. As you can imagine, being Director General of our organization and being able to welcome you for a press conference reporting on a very important scientific discovery is something that makes me feel very happy, and I hope it's only the first one in a string of many more discoveries that will come in the future, I hope. As you know, ESO is the most productive ground-based observatory in the world. We operate some of the most advanced astronomical instruments in some of the best astronomical sites imaginable, and we're actually in one of them today. You're about to hear about the history of a truly groundbreaking discovery that highlights ESO's capability of bringing those instruments to the service of science and to the service of our community, together with, of course, the discoveries from other facilities, in this case, the gravitational wave observatories LIGO and Virgo. So I'm very proud of the role of ESO on this particular discovery, and I'm sure that when you hear about it, you will be as excited as we are here in Paranal, because we have the feeling that we are actually opening a new door into the discoveries of the universe. So thank you very much and welcome.
Thank you very much, Xavier. Now we welcome Stephen Smart from Queen's University in Belfast, who will give the first presentation and introduce what we're going to hear today. Stephen.
Good afternoon, everyone. So 100 years ago, Albert Einstein predicted the existence of gravitational waves. So these tiny ripples in space-time, he predicted from his theory of general relativity, could be caused by accelerating massive objects, and those might be merging neutron stars or black holes in binary systems. But he thought at the time that the signal on Earth would be too small ever to be detected. But 100 years later, in a remarkable and still to me amazing physics experiment, the LIGO and Virgo collaboration did detect gravitational waves. 2 weeks ago, the Nobel Prize for Physics was awarded to 3 of the founders of LIGO. But of course, this Nobel Prize was recognition of a huge, talented international team of over 1,000 scientists who built these amazing machines and made this discovery possible. So, of course, Einstein's theory was correct. Gravitational waves do exist in the universe. They are produced by massive accelerating objects, and 4 merging black hole systems have been found to date. So we are here today at ESO to hear about the next chapter in this momentous story of physics and astronomy. So this is how it happened. On the 17th of August this year, at 12:41 Greenwich Mean Time, the LIGO-Virgo collaboration announced a detection of a gravitational wave source. Now, they had 4 detections of binary black hole mergers to date, but 2 things made this discovery stand out. The first one was the length of the signal. It lasted for more than 60 seconds. If you compare that to the binary black hole mergers, they lasted less than a second. Also, 2 Earth-orbiting satellites, NASA's Fermi satellite and ESA's Integral satellite, detected a burst of gamma rays just 2 seconds after the gravitational wave source, and in approximately the same area of sky. So at that time, astronomers got very excited because having this long-duration gravitational wave signal and a burst of gamma rays suggested that this may not be a binary black hole system, but might be 2 neutron stars merging. And that gave us the opportunity to search for directly an optical and infrared counterpart that would exactly pinpoint the position in the sky of the gravitational wave source. But at that time, the region on the sky was known to about 100 times the size of the full moon. So at 12:41, when the signal came, Chile was in daylight. The signal came from the southern hemisphere, so the Chilean telescopes were very well placed to observe. But at 12:41, it was still daylight in Chile, and none of the ESO telescopes or any of the Chilean telescopes could observe at that time. Within 11 hours, the LIGO and Virgo collaboration had refined their localization map, refined it such that a search for an electromagnetic counterpart became feasible. And at about 23:45, just as dusk fell in Chile, many telescopes in the high Atacama Desert searched this localization region to see if they could find an electromagnetic counterpart. At that time, as I said, the size of the localization region produced both by LIGO and Virgo and by the gamma ray satellites was the size of about 100 full moons, so still quite challenging. This shows you a movie of the whole sky, but zooming into the region that LIGO and Virgo localized at the time, you'll see the contours pop up here. So within these contours, what several telescopes in Chile did, and 6 or 7 telescopes, they took 2 strategies. One was to map out the whole region. Another one was to say, well, let's look at the biggest, brightest galaxies in this sky localization region. That's where all the stars are. That's maybe where this potentially merging neutron star system is coming from. You can see a zoom in here of the galaxy, NGC 4993. Very quickly, just within the first hour of observing, 7 telescopes localized a new point source of light in this galaxy, NGC 4993, and I'm going to show it to you here. So this object here is the first optical and near-infrared counterpart to a gravitational wave source. This is what caused the gravitational wave source in August 17 and the gamma ray bursts that we saw. The reason that we know that is that this galaxy, NGC 4993, it's in the sky localization region. It's also at exactly the same distance that LIGO estimate the gravitational wave signal came from. This galaxy had been observed about 1,000 times before over the last few years with no sign of this point source. It popped up within the first night of observing. Also, what made this unusual was that, and I'll show you a movie here of the evolution. So ESO's telescopes over the next 2 weeks, over the next 2 to 3 weeks, observe this object every night. It's possibly the most unusual flash in the sky that we have ever seen. Let me show you now a movie. I zoom in. The object started off in the first few nights very blue and hot, and you'll see the first image pop up here. We saw it blue within the first 24 hours. As it evolved over the next 2 weeks, it faded very rapidly, and it became red very rapidly. So this fading and getting red very quickly is actually unprecedented for transient objects in the universe. We find supernovae all the time. There's a supernova every second in the whole universe. This looked nothing like the supernova that we find in the local universe. It faded within 3 weeks. It got red extremely quickly. We had a gravitational wave detection and a burst of gamma rays. This source, the fading and the rapid reddening, almost exactly matched the models that were produced for merging neutron stars. These models predicted that heavy chemical elements would be radioactive and would produce a glow that would last for 2 weeks and become red very quickly. And this is exactly what we've seen. This type of object has been termed a kilonova, and this is the first discovery of one. So today, ESO and European scientists have played a central and critical role in this discovery. And my colleagues today are going to take you through some of the fascinating physics and astrophysics that have been enabled by this discovery. Thank you.
Thank you very much, Stephen. It's a remarkable discovery. We're now going to hear from Samaya Niskanka, who will tell us more about the gravitational wave part of this discovery. She's from Radboud University in the Netherlands and is also part of the Virgo collaboration and an expert on gravitational waves.
So, good afternoon, everyone. I'm absolutely delighted to be here this afternoon and to spend it with you. Let's begin. So, on the 1st of August 2017, the two LIGO detectors located in the US were joined by the new kid on the block, the Virgo detector, which is a European-led interferometer located in Pisa, Italy. And incredibly and amazingly, within 17 days of Virgo joining the observing run of the LIGO detectors, we observed gravitational waves from an entirely new type of source, a pair of neutron stars that were essentially losing energy due to the in-spiral from gravitational wave emission that happened 130 million light years away. So there are two important things I'd like to stress. Number one, this was the strongest gravitational wave signal that we've ever measured. And number two, until now, we've only observed binary black hole mergers through their gravitational waves. So, what are these detectors? These detectors are L-shaped laser interferometers, which are 3 or 4 kilometers long in arm length. And essentially, a laser beam of light is generated. It's directed towards a beam splitter, which then splits the light beam into 2 equal and separate beams. And each beam is then perpendicularly directed to a distant mirror along these kilometer arm lengths and reflected back to the beam splitter. And so essentially, when these gravitational waves passed through this measuring device, we were able to actually measure and monitor the stretching and squeezing of the arm length due to this gravitational wave. And so we were able to actually monitor the flickering of the light collected at the detector. And so by digitizing and analyzing this flickering of the light at the detector, we were able to actually analyze the signal and compare this to models of theoretical predictions of the gravitational wave. And so these are the most precise measuring devices that we have built. We can measure distances 1,000th the diameter of a proton. So essentially, if you want to measure the distance to our nearest star, which is 4.3 light years, with these detectors, we can do this to the width of a human hair. So for me, that's mind-blowing in itself. So let's look at the gravitational wave signals that we have detected so far. And so shown in the top are the gravitational wave signals, these distortions in space-time from the binary black hole mergers that we have seen so far. And shown in bottom in this animation in yellow is the gravitational wave signal from this new binary neutron star. And notice how it lasted 60 seconds compared to the 0.2 seconds that was measured for the first binary black hole merger. Okay? Another thing I'd like to stress is that note as time moves forward, you'll see that the size of the signal and the frequency of the signal actually increases. Yes, and so this is what we call this characteristic chirp, when we can hear gravitational waves in the violent universe. And these characteristic chirps have so far been consistent with Einstein's theory of general relativity. Now, from these wiggles and chirpy signals, we could actually infer that the source was this binary neutron star, where each of the individual masses of the neutron star ranged from 0.86 to 2.26 solar masses, so times the mass of the sun. The size had characteristic radii of about 15 kilometers, so that's essentially the distance from Garching to Munich. Excuse my German accent, but I traveled this distance last night to get here. And of course, this makes the density of these objects so high that basically you can cram the entire of humanity into a sugar cube. Okay, so these make these neutron stars the most remarkable extreme gravity siblings to black holes. So, shown in orange in this plot are the neutron star masses of the system that we have detected in gravitational waves. And you can compare this to the black holes that we have measured in gravitational waves in blue. And it's interesting to contrast this to the neutron star and black hole masses that we have inferred previously from electromagnetic observations that are shown in yellow and purple, respectively. And there are two things I'd like to stress. Number one, we're uncovering this diversity in the fundamental properties of these extreme gravity sources and systems. And secondly, we don't actually know what the remnant of this neutron star binary was. Was it a black hole or a short or long-lived neutron star? This remains an open question and an exciting one. So how well could we actually localize these events from gravitational waves in the sky? And so this was obviously fundamental to actually following up the source and finding the counterparts in the optical, X-ray, and radio. And so essentially, it's important to bear in mind that these laser interferometers are all sky detectors in some sense. They have very poor angular resolution. So in order to actually reconstruct where the event happens in the sky, you need to have a network of 2 or more detectors. So these big, smiley bananas in colors show the sky errors for the binary black hole mergers that we have detected so far. And they span hundreds to 1,000 square degrees. Remember that the moon occupies 1/4 of a square degree on the sky. Okay, so for the first binary black hole merger shown in green, in that volume, there were 100,000 to 10 million galaxies. So essentially, it was very hard to say where did this binary black hole form, as well as how did it form. And of course, the big game changer and the exciting news today is that we have a third detector, the Virgo detector, which enabled us to localize this new event shown in this yellow golden blob here to 30 square degrees. So really, this is incredible. And finally, I'd like to end with an animation that shows how we were actually able to pinpoint the exact location of where this gravitational wave event happened. with the LIGO-Virgo detectors as well as space and ground-based facilities. So shown in this animation is the 1,100 square degrees that Fermi was able to localize this event. If the two LIGO detectors had been operating, we would have been able to localize this to 190 square degrees. But with the 3 detectors, we could do this to 30 square degrees. And in this gravitational wave volume, there were 49 galaxies. So this enabled some of the optical telescopes that went and actually hunted out the precise position of where this event happened, and a very, very nice and clean strategy to actually localize the host galaxy of this event.
Thank you very much, Samaya. Now we're going to hear from Marina Rekuba here at ESO, who's going to tell us about some rather exciting events that happened at ESO after this event emerged.
Thank you very much. Good afternoon. So in the next few minutes, I will tell you how ESO reacted to the detection of the new gravitational wave. It is really great pleasure for me to be here because at that time, actually, I was on Paranal when the first trigger arrived. And we were told to point the VISTA telescope, which has a very wide field of view, to search for this new source. At the same time, we could very flexibly reschedule our observations. And at the very end, once the source was known, in the next days, we went back over and over again, observing it over a full wavelength range, simultaneously using many different instruments. And this was really important in order to pinpoint what is the physics behind this kilonova. So here we are in the middle of Europe, and one of the most light-polluted areas. The observatories are in the northern Chile, and the 2 observatories that I will be talking about today mostly are La Silla and Paranal. In La Silla, there are several 2 to 4 meter telescopes and another host of smaller domes that are observing specific experiments looking for exoplanets, planets beyond our solar system, or scanning wide areas of sky looking for new sources that change brightness or just pop up like this gravitational wave source appeared. On Paranal, we have the VLT 4 8-meter class telescopes with some of the most modern instrumentation, as well as 2 survey telescopes, VST and VISTA, that were all involved in this discovery. The telescopes are working 365 days a year. The scheduling is very complex. We have many different projects that are using different instruments that you can see here in this very colorful slide, each instrument, each project, different color. But we also reserve some time for flexible dynamical scheduling when we can observe programs according to their priority, according to the current observing conditions. In this way, we can react very quickly to unexpected events. ESO has introduced the so-called target of opportunity observing proposals, where astronomers can request to observe a certain target. They know what they are looking for. They're looking for a kilonova, but they don't know where or when. So with the discovery of the gravitational waves, we got proposals, requests to schedule these observations in a flexible mode, and we were ready to do them as soon as the first gravitational wave with this long duration was discovered. On the 17th of August, we received by email notification that there is this new gravitational wave discovery. We immediately pointed VISTA as soon as the night fell and we could start guiding. We scanned a pretty large area on the sky. VISTA has 1.5 square degrees. That's 3 full moons field of view in just one shot. We With VISTA, as well as with several other telescopes, the location of this new source on the sky has been found. And the next day, all the other telescopes and instruments were just thrown into this. And we started observing with around NGC 4993, looking for this signature of the kilonova. So the range of telescopes, here we can see them in different colors. From the survey telescopes on the top, the blue, the VLT, the NTT, the MPG ESO 2.2 meter, and the REM, they were all used, and also ALMA, they were all used to observe this source. And really the key factor here is using them simultaneously. This source, it was in the southern hemisphere, but it was rather close to the sun, and it was setting fast. So we could only observe it for about 1 hour in the beginning of the night. And as the time went, each day it was even shorter. So it was really important to observe with all of these different instruments and to get the whole range of properties from the near ultraviolet to visible to infrared, to get images, to get spectra, polarimetric measurements. Over the course of about 2 weeks, a little bit more than 5,000 scientific images and spectra were collected. More than 115 hours of observations, 14 instruments, 7 different telescopes. And again, all of it simultaneously, every night, following this kilonova and pinpointing down its physical properties. Thank you.
Thank you very much, Marina. Now, we've heard neutron stars mentioned many times, and now we're going to find out a bit more about them from Elena Pian from Bologna, who's going to tell us what we learn and why they're important.
Thank you very much. Good afternoon. So indeed, which astrophysics have we learned here? Let's go a little bit more in detail. Let's investigate in some more detail these double neutron star mergers and their relevance, their astrophysical relevance. So it all starts with massive stars, namely stars larger than 10 solar masses. Massive stars usually come in binary systems. When the core of a massive star exhausts its fuel, it collapses under its own gravity, and this collapse drives a supernova explosion. The remnant of supernova explosion is a neutron star. So when both members of a binary massive system go supernova, what's left behind in the end is a double neutron star system. And this is what we have here. So supernova, you see it here, supernova-like curve in optical are red and blue bands and neutron star merger, neutron star system left behind. The two neutron stars rotate one about the other for hundreds of millions of years. And they lose energy in rotating. They lose energy via gravitational radiation. As an effect, as a consequence, the orbit shrinks. They get closer and closer to one another. They rotate even faster. In the last phase, they rotate dramatically fast. They reach a rate of rotation of 1,000 cycles per second. When they touch each other, they merge and explode. This drives an explosion. The energy and neutrons densities in that moment are so high that new atoms, heavy atoms, can be formed. And you see here some of them. Some of them are rare, notably gold. It's fake. It's fake. No problem. I mean, we are at ESO. This is not a bank. So they build telescopes. They don't have gold bars. But on the other hand, some of you today may wear a piece of jewelry made of gold or platinum or a wedding ring. This is where all that gold and platinum come from. And this is why it's getting interesting. So For visual impact, I've reported here the periodic table of elements, where all elements are color-coded according to their formation channel. In purple, you can see the elements that formed via binary neutron-star merger. And as you see, they are all heavier than iron. Some of them are quite heavy. And of course, you can see also platinum and gold over there. So how is all of this relevant to us? How does all of this relate and connect to what we have done, our observations? What have we done? On the left, you see the image, again, of NGC 4993. The source is top left. We've used the Very Large Telescope with the X-shooter spectrograph to take spectra. The way it works, the X-shooter has a device by which it can isolate the light of the source you are interested in. It's represented here with that rectangle. So once you've done that, you have the source, and the spectrograph disperses the light of this source from ultraviolet to near-infrared. And what you get is here. It's coming. This is the sequence of spectra we have taken with X-shooter for 1 per day, for 10 days. What is this light? This is the kilonova. What is this light? The kilonova light is radioactive light. Those atoms that have been produced, that have been freshly synthesized during the merger, are unstable. Many of them, most of them, are unstable, and they decay radioactively. Radioactive decay powers this kilonova object, powers this source. The light that you see is radioactively produced. The first spectrum, the brightest one, it's very bright in the optical. It has the shape, it's the spectral shape of a star. Namely, it's an almost purely thermal spectrum. It's the spectrum of a source that emits just by virtue of its temperature, which is about 5,000 Kelvin. What does this mean? It means the source at the beginning, this is 1.5 days after explosion, so it's very early on. At the beginning, the source is so tiny and so compact that no single photon comes out from its interior. So what we see is just the outer hot surface of this source, its photosphere. Then the matter becomes less opaque. It expands quite fast, in fact. Material expands at 20-30% of the velocity of light here and becomes more transparent. So the subsequent spectra you see deviate more and more from the first one, are more and more different. And they develop some features, you see some features that are directly connected, that are produced by the freshly synthesized, freshly formed heavy atoms. So if we are able to associate each of these features with specific atomic species, we will be able to tell which precise atoms have been produced and their proportions, their abundances. So why is this different? Why is it fundamental new progress? How is this different from before, from what we knew before? The point is that all gravitational signals that have been detected by LIGO Virgo before this one were produced by double black hole mergers. Those detections have told us unambiguously, beyond ambiguity, that stellar-sized black holes do exist. There's no nucleosynthesis associated with double black hole mergers. This present case is different. This is a double neutron star merger. This neutron star merger, we have demonstrated, is a factory of heavy elements. This is why it is so important. So by studying these sources, we are in a position to reconstruct precisely the history of heavy element evolution in the universe. And so this is what we plan to do, both studying better this object and future objects that will be detected during the next, hopefully be detected during the next LIGO Virgo scientific runs. So we are working, stay tuned, and thanks for your attention.
Thank you very much, Eleanor. Unfortunately, you don't get to keep the gold bath, but... Our final speaker is Andrew Levin from the University of Warwick, and he's going to summarise the results and also look forward to tell us what's coming next.
Okay, thank you very much, Richard. So it's a pleasure to be here in Garching today, and as Richard says, I'm going to try and wrap up and talk about what we might do in the future as we detect more and more gravitational wave sources. So, over the course of the last few weeks, we have really acquired a set of unprecedented observations. And those observations have allowed us to answer at least 3 questions that have been challenging astronomers for decades. In particular, we now know that we can observe the merger of 2 neutron stars, both with gravitational waves and with visible light. That 2 different messengers, a photon, a bit of light, and a gravitational wave, can travel to us from 130 million light years away and be observed on the Earth. We also now have solved another 40 to 50-year-old problem because we have understood what it is that makes short-duration gamma-ray bursts. It is merging neutron stars. And as Eleanor has just talked about, we have also understood where the heavy elements that we see on Earth and across the universe have actually come from. And that might sound like the end of the story, but it's not. It's really the beginning of the story, because this combination of gravitational waves with light will enable us to open a whole new area of astrophysics and answer questions that we have been unable to access until now. And there are many things that you can do, and I'm only going to touch on a few of them. Perhaps chief amongst them is to look for the third kind of merger. That is to say that gravitational waves can be detected from binary stars that contain either neutron stars or black holes. In 2015, we observed black hole mergers for the first time. In 2017, we have observed neutron star mergers for the first time. What we have yet to observe is the merger of a neutron star and a black hole. And that is what you're seeing now in this simulation. And when you have a neutron star merging with a black hole, you have quite different masses involved. The neutron star is perhaps a little bit more than the mass of the Sun. The black hole might be 10 times the mass of the Sun. And so the process of the merger in gravitational waves and the output in light might be very different. And so when the LIGO and Virgo detectors resume their science run about a year from now, something we will keep our eyes peeled for with the ESO telescopes is the counterpart to a black hole neutron star merger. Returning to the question of the heavy elements, there are many more questions that we can answer there as well. We now know beyond doubt that this merger created many heavy elements. But when we look around us in the universe, we would like to know, do these mergers create some of the heavy elements, most of the heavy elements, or all of the heavy elements? And accessing that is quite hard. And that's not surprising, because when you make these elements, you do it by merging 2 neutron stars together, throwing out perhaps 1% of the mass of the Sun in neutrons at 30% of the speed of light, and then you observe the mixture of elements that are seen. And so it's going to take work from observers and from theoretical astrophysicists to try and unpick exactly how much of each element was produced. But for example, the figure we have here shows how much of different elements you would produce if this merger actually pushed out the same relative quantities of the elements that we see around us in the solar system. And for example, that tells you that most likely this merger made the mass of the Earth in gold. And that's quite a remarkable thing to think about. You'd be rich if you could somehow pocket that. But we also want to know not just about how much each individual element puts out, but whether these are common or rare occurrences. Because if they are to create all of the heavy elements, they need to be quite common. And so we need to understand where and when in the universe they happened. And to do that, we simply need to observe more examples with visible light and gravitational waves. And then a final thing that I want to talk about is a rather different thing that you can do with gravitational waves, both now, has been done, and in the future. And that is actually to use them as a yardstick to measure the universe itself. And the merger of two neutron stars is something that we know how loud it should be in gravitational waves. And because we know how loud it should be, we can measure how loud it appears to us and use that to infer the distance. It's something called a standard siren. And that means that gravitational waves provide a new and completely independent way of measuring distances across the universe. And when you have a gravitational wave and you have a counterpart in visible light, you can compare the distance that you get from gravitational waves with the velocity of the galaxy that you measure from visible light. And distance and velocity, as Edwin Hubble showed in the early 1930s, are in fact strongly correlated. So the further away a galaxy is, the faster it moves away from us. That's Hubble's law, and it's the evidence for an expanding universe. And so gravitational waves offer us a new way to do this and actually allow us, even with one event, to measure the rate of expansion. That rate of expansion is a number called the Hubble Constant. And it's quite important still to measure the Hubble Constant because the two pillars on which we currently measure the Hubble Constant with visible light and with the cosmic microwave background actually don't agree with each other. And so a third completely independent method will ultimately be very, very powerful as a route to understanding the scale of the universe. And in the future, perhaps with the next generation of interferometers, combined with new extremely large telescopes on the Earth, you might be able to do this and measure the expansion history of the universe well beyond halfway back to the Big Bang. So the last few weeks have been pretty momentous for astronomy. That combination of gravitational waves and light, or perhaps more simply sight and sound, really gives us a whole new view of the universe and a new way to appreciate it. And you can see that in everyday examples. So a momentous event in my own life in the last few weeks has been the birth of a child. And when you're in the delivery room and your child is born, you don't just want to see the baby, but you wait to hear the first cry that says, yes, I'm here and all is well. And it is the combination of sight with sound that enriches that experience for us, in the same way that that combination of sight and sound, or light and gravitational waves, enrich our view of the universe. So really, this is the birth cry of a new way to do astrophysics. So I will finish there. Thank you for your time, and say welcome to the era of multi-messenger astronomy.
Thank you very much, Andrew, and thanks again to all our speakers for some really impressive presentations. We're now going to have some questions, and we'll start with questions from journalists in the room. And if you'd like to ask one, please raise your hand and state what media outlet you're from. So do we have someone to start? We will have some questions online as well. No questions? No. Well, maybe I'll move on in that case to... we have several that have come in online. And let me see. In fact, quite a lot. We had one from Rashmi Shivna, who's from PBS, Washington, D.C. And he says, scientists saw signatures of recently synthesized heavy metals like gold and platinum, which basically solved the long mystery of where half of all elements heavier than iron are produced. So can we predict the frequency of these neutron star mergers based on the proportion of heavy elements we see in the universe? So maybe Andrew, take that one.
So it's a very interesting question, and there is, of course, a big challenge that until right now we've been unable to really understand exactly where the very heavy elements in the universe come from. But I think we can make an assumption that these things are all made from these very massive binaries which emerge ultimately as neutron stars. And in that case, then you probably require about one merger in the Milky Way every 100,000 years. But the uncertainty on that is quite large. I think what is quite clear now is that you do need to have these heavy elements made by events which actually create quite a lot of heavy elements, perhaps 1% the mass of the sun in heavy elements, but do so quite rarely. And there is evidence of that from very stars across the Milky Way, and actually from looking at sediment on the seafloor.
Okay, thanks very much. Right, we now have a question from something called the Hole in the Universe blog, which I've never heard of, but it's a good question. And it is, what's the significance of detecting a gamma ray burst? How does the gamma ray burst fit into this picture? Why do they give off gamma rays? And what do we learn from that?
This short gamma ray burst detection has been particularly important because it allowed us to make a breakthrough, to confirm something we've always suspected, that short gamma ray bursts as well as long gamma ray bursts are produced by jets. And we usually, because of enhanced luminosity and selection effects, we see those gamma ray bursts that are located at cosmological distances and are Doppler favored, as it is said in jargon, namely they have jets pointing at a very small angle with respect to the observer, so their luminosity is enhanced because these jets are relativistic. Now, this particular gamma ray burst was not bright at all, and it was close by because it was associated with this gravitational wave signal. Its X-ray counterpart bears the signature of a off-axis jet. It's clear from the X-ray afterglow that this X-ray counterpart is produced by a jet oriented at a large angle with respect to the observer, which is why we observed it was dim. When we observed it was dim. If it was located 10 times, if it was 10 times more distant, we wouldn't have detected it. So we have proven that gamma ray bursts misaligned, namely oriented at a large angle with respect to the observer, do exist. So as we say, we have reconstructed the so-called unified scheme for gamma ray bursts. We have seen a gamma ray burst, a misaligned one, not just the usual gamma ray jets pointing toward the observer. We know for sure now that short gamma ray bursts and presumably long gamma ray bursts do have relativistic jets.
Thank you very much. I have a question now which is about future merger events. It's from someone in Cyprus who asks, how are you planning to streamline and expedite the pinpointing of the source for future merger events? In effect, how do you plan to increase the directional resolution of the gravitational waves detected, and how will the optical follow-up be done? Who wants to take that?
Press the button.
Just one.
So we are planning to improve the sensitivity of our detector by improving the suspension of Virgo. We are increasing the light, and we will plan to do a joint run at the end of the next year. So the date is not fixed yet, but about the EM follow-up, I don't know if you want to.
So I think this discovery, so with the EM follow-up, we're mostly limited by access to telescope time. You can see that the critical thing here was to react within 24 hours and get as many observatories looking at it within the first 24 hours. So I think this discovery shows us that the scientific return of making that investment of time and effort to observe immediately over the first 24 hours with nearly every observatory in the southern hemisphere plus satellite telescopes is worth the effort, and the scientific return is huge. So I think that will motivate people in the optical and at other wavelengths to follow all of the nearby LIGO discoveries that look like they may be neutron star mergers or neutron star black hole mergers.
And maybe I can follow up on this comment. So in terms of actually improving the angular resolution from gravitational wave detectors, there are really exciting projects that are going on, that are happening right now. A new advanced detector is being built in Japan, in the Kagra, it's called Kagra, in the Kamioka mine. And so that's happening right now. The aim is to actually reach comparable sensitivities as we've seen now in 2020. There's also a very exciting new project called LIGO India. And the aim is to actually go online there by 2022 and 2023. So we'll actually see the resolution of the sky errors from 3 detectors going to 5 detectors, improving by about a factor of 5. Okay, and really the big impetus here is to improve the resolution to do EM follow-up. The second point is about the latency. So the aim from the LIGO-Virgo collaboration is really to try and push to send out alerts of these sky errors within the minute's time scale. So here it's really being able to also characterize the glitchiness that we see in the gravitational wave detectors. I didn't talk at all about all the different sources of instrument noise, but to be able to say, yes, that was an astrophysical signal, and then be able to actually send out these alerts without having too much human involvement, which is really, I think, the main limiting factor, is that, we have a lot of humans involved in the loop just to make sure that these alerts, are being sent out and are not related to glitchy instrument noise.
Thank you. A question now about what's left over after this event. The question is there really no way to find out what sort of remnant was left behind?
You can go first.
Well, one of the evidences for what has been left behind comes from the spectra, from the analysis that Elena was talking about. Mm-hmm. And as Samaya pointed out, from the gravitational wave itself, from the chirp, we cannot really know what's left behind, right?
Yes, so the fact that this system actually merged, probably, in order to say something about the remnant, we have to look at sort of the kilohertz, 6 kilohertz or so point in the frequency, and this is where the sensitivity of our detectors is really, really limited. So we haven't been able to say anything about the remnant. My hope is that potentially from the electromagnetic signatures and combining this with the gravitational wave information, we may be able to actually say something about whether it is a black hole or a short or long-lived neutron star. I think what we can say is that it's not a highly magnetic, rapidly spinning neutron star like a magnetar, because there, the EM light curves that we would have seen would have been significantly different.
Thank you very much. I've got a question now from a high school in France, and it's quite an intriguing question, actually. They say, we learn in high school that electromagnetic waves are made of photons. Could you tell from your experiments if gravitational waves are made from quanta, and how many of them do you collect in one detection? I think lots is not a viable answer.
So I would say that so far our gravitational wave observations have been consistent with the spin-tooth tensor theory, general relativity essentially. So so far I would say that gravitons do appear to be the quantized unit for gravitational waves. With this new event, we were actually able to do quite interesting new tests of the speed of light, for instance, by comparing the arrival times of our GRB signature as well as our gravitational wave. So there is a whole host. With regards to the number of quanta, I have to say that, I'm quite sleep deprived after 2 months of solid work and non-stop work. But what we have been able to say is that comparing to numerical relativity simulations, the energy released from this merger, even if we didn't actually see it in band, we can put an upper limit of 0.025 solar masses. So that's what we've been able to say. So, Magdalena? Yeah.
Okay, thank you very much. I have one or two more, but are there any from the audience? Come on, there must be somebody here. Ah, yes.
The signal was very long, very interesting, more than 60 seconds. So what does this mean? Does this mean that it was a slow merger? Is it related to mass, or is it something more special? Is intrinsic to neutron stars?
So, it's me again, sorry. So, in the frequency band of these advanced gravitational wave detectors such as LIGO and Virgo, essentially you are sensitive to the different masses of the progenitor system. So in the case of heavy stellar mass binary black holes that we saw in that frequency range, we were sensitive to essentially tracking the evolution of the final few orbits, the merger, and the ring down of these systems, yes? Whereas for this case, because it was much lower mass, in terms of the total mass of the system, we were sensitive really to the in-spiral, so really these thousands of orbits that we were tracking in band very carefully, the size of the signal as well as the actual phase of the signal. And so we were very sensitive to measurements of the combination of the two masses of the progenitors. So that really is the big change in terms of, what do you gain by tracking, many, many thousands of orbits of this system, as opposed to having measurements of the actual remnant, which we had in the binary black hole case.
Thanks very much. I've got a question here from Elizabeth Pearson, BBC Sky at Night magazine, and she says, this feels like a new dawn for astronomy. What are the next big discoveries that gravitational wave astronomers have their ears out for? As opposed to eyes, presumably. Yeah, makes sense.
So I think, we mentioned the idea of a merger of a neutron star and a black hole. And I think there's a lot of new things that you can learn with that. And in particular, because a neutron star, when it comes in close to a black hole, it doesn't actually just get swallowed whole. It sort of gets shredded up into pieces. And so there's a lot of new things that you can do with that, both in terms of the signal from gravitational waves, but also from the actual amount of neutrons that are kicked out. It might be a lot more than in a neutron star merger. So I think top of my wish list for the next run would be a black hole neutron star merger.
Can I maybe follow up as well? Sorry. And the other thing I'd like to stress is another exciting potential source is if we have a galactic supernova that goes off, which is asymmetric. So I think that's another thing that will be very interesting for astronomers in terms of seeing and hearing these events. And I think particularly exciting is that, we are, probing this entirely new part of this gravitational wave spectrum. So really it will be the unknown discoveries that really excite me, I think, that get me up in the morning, will be what will those gravitational wave detectors see that we didn't predict before, and that, we will have all these incredible additional puzzles to actually go ahead and solve.
Well, thanks very much. I think we're just about getting to the end. I'd like to thank the panelists again, both for their interesting talks and interesting replies to questions. And I'd like to thank everyone for joining us, particularly the much larger number of people who are online. So this conference is coming to an end. There will be some drinks and very light refreshments available for the people in the room, but I'm afraid people online will have to get their own. But thank you. Thank you very much for coming. I think it's been an extremely interesting day and a very exciting moment. So thank you very much. And before you go, one final thing. We're also organising a Reddit Ask Science Ask Me Anything session online tonight at 18:30, and the link is up there. So that would be a chance to pose more questions to a larger group of people online. So that's the next step. Thanks again.